Hey AP Chemistry, as a request I wanted to show you how we could work through question number 18, and then I'm going to give you a sneak peek at how I would apply that to something like number 20. Okay, so we're given two rate constants at different temperatures and we want to know what the activation energy is. Well, I gave you this equation, natural log of K2 over K1 equals EA over R 1 over T1 minus 1 over T2. Now, they have the numbers 1 and 2. It does not matter what you label as 1 or 2 as long as you are consistent with the T1 and the K1 on both sides. So if I'm going to arbitrarily say my first one is 1 and my second one is 2, now here's my T1, here's my T2, here's my K1, here's my K2. Also, a little aside, we need to make sure that our temperature is in kelvins. So I'm going to convert this first temperature from 30 degrees Celsius to Kelvin, which is adding 273. So that's 303 Kelvin is my first temperature. And then adding 273 to 49, 322 is my second temperature. Okay, and so now I'm going to plug these numbers into this equation and try and solve for, it's asking for the activation energy. Side note, R is equal to 8.314 joules per mole Kelvin. So that's the value of R that's going to go here. The only unknown in this chemical equation is EA. So if I start plugging in these numbers, natural log of K2, right now remember, I established my second one is 2, and my first one is 1 here. So my K2 is going to be 1.21 times 10 to the minus third per molarity per second over 1.38 times 10 to the minus fourth molarity per second. Now, it does not matter if you label this one as 1 and this one as 2. You can have this upside down, but then your temperatures are going to be opposite. Okay? But I'm going to be consistent. I'm looking for EA. I'm going to plug in 8.314 joules per mole Kelvin. And then 1 over T1. T1 I established was 303. So 1 over 303 Kelvin minus 1 over 322 Kelvin. And notice that my kelvins ended up in the denominator. So that's going to give me units of per kelvins. Okay, now if I solve for everything, right, and I do it bit by bit, let's say I just solve for what's 1.21 times 10 to the minus third divided by 1.38 times 10 to the minus fourth. This value is equal to 8.77. So now I'll have natural log of 8.77, right, this whole thing, if I plug it into a calculator, is 8.77, equals EA over 8.314 joules per mole Kelvin. And I'm going to solve for these parenthesis calculations. So 1 over 303 Kelvin is, if I solve for that, I get 0.00330 per Kelvin. And if I solve for 1 divided by 322, I get 0.00310 per Kelvin. Okay, so I just did the math. I did 1 divided by 303 in the calculator, and I did 1 divided by 322 in the calculator, and now I'm going to subtract those two numbers. And if I bring it down, I'll get 0.000195 per Kelvin. Okay? So I just did that with the calculator. So if I plug that into a calculator, boop-a-doop, these are the numbers that I got. Now, the question wants you to solve for EA, so I have to isolate this EA, okay? Now, I could easily just do natural log of 8.77. That is equal to 2.17, right? So if I plug that into a calculator, I do this. I get 2.17 equals EA over 8.314 joules per mole Kelvin. 0.000195 per Kelvin. Okay? So when I say natural log of 8.77, this is a function in the calculator. So if you look on the calculator, there is literally a function that says ln, and I'm just going to, like I did before, I did ln of 8.77, and I got my 2.17. Okay, so now I'm trying to isolate this EA. I have EA divided by 8.314, and I have EA being multiplied by this 0.000195 per Kelvin, right? And how did I know that it was being multiplied? Well, I had EA over this, and it was being multiplied times this whole parentheses, and I turned this whole parentheses into just one number instead of it being in fractions. And so now, if I want to isolate EA, I could just divide both sides by 0.000195 per Kelvin. 0.000195 per Kelvin. And so I'll get 2.17 divided by 0.000195 per Kelvin equals EA over 8.314 joules per mole Kelvin. Okay. And now if I want to isolate this EA, I could multiply both sides by 8.314. If that's not the step that I choose to do, maybe I just want to do 2.17 divided by 0.00195. I could do that. So if I just give me more paper here. So if let's say I solve for this, if I plug this into the calculator, I'll get 11128.21. And this per Kelvin means I have one. This is the same thing as saying 1 over Kelvin. And since it's in the denominator, now it becomes the numerator. So this 1 over Kelvin just became Kelvin on top. And that's why this number has units of Kelvin. If you don't know what I mean right here, check one of my previous videos where I did fractions and units. And now I have EA over 8.314 joules per mole Kelvin. And now how do I solve for EA? Since I have EA divided by 8.314, I have to do the opposite of dividing 8.314 to get EA by itself. I have to multiply both sides by 8.314 joules per mole Kelvin. And then multiply this side by 8.314 joules per mole Kelvin. Okay? And so in doing this, I'll be left with this. And so now I'll have EA equals, if I solve this math here, if I do 8.314 times my 11,128.21, and notice how this is joules per mole Kelvin and this is Kelvin. These Kelvins will be able to cancel out, and check my previous video on how that happens. And I get quite a large number, 92,519.89 joules per mole. Now, if you look at the choices said 92.7 Kelvin, 300 kilojoules per mole, 343 kilojoules per mole, 200 kilojoules per mole, 40.3 kilojoules per mole. What's the problem with our units and the units in the problem? And this is something that you have to be cognizant on the AP exam or even just any exam. Units. So I have joules here and I want kilojoules. There are 1,000 joules is equal to 1 kilojoule. So if I want to do this, I'm going to show you doing this dimensional analysis. It's the same thing. You just divide by 1,000. But just in case, if I have joules per mole, if I multiply by 1 kilojoule divided by 1,000 joule, my joules will be able to cancel out. And then this is just dividing by 1,000. So if I want to go from joules to kilojoules, you divide by 1,000, I will get 92.52, if I'm rounding, kilojoules per mole. And if you look at the choices, you have 92.7 kilojoules per mole, which is choice A. Now, rounding and however many significant figures will have us off by that plus or minus 0.1, that's fine. Okay, and then to end, connecting to question number 20, question 20 gives you K1 and K2, and it gives it to you at different temperatures. So K1 would be 0.000 122 per seconds, and this is at temperature of 27 degrees Celsius, which needs to have that in Kelvin. And then K2 is at 0.228 per seconds, and that temperature is at 77 degrees Celsius, which need to bring that to Kelvin. If I want to solve for this, this is 2 steps. Part 1, I need to solve for EA, just like I did in this example. And then part 2, use the EA that you solved, make sure it's in joules per mole, and then solve for a new K. So when you set it up in the end, you'll have like natural log of, you could use one of these values, let's say I use this one, 228 per second, K2 over K1 equals the EA that you get. And if you want to check your work, and I could post, I'm going to share my answer key, but if you want to check your work, the EA that you should have got for this was 131,521.89 joules per mole. That's what you should have got for question number 20, divided by 8.314 joules per mole Kelvin. And you're going to have 1 over 2, I used a different one, but you're going to have 1 over the 290 minus 1 over the, 1 over 290 minus 1 over 350. Okay? So in the end, you're going to solve for something like this and solve for K1. And remember, this is all just math here, plugging and chugging, and you're going to be left with natural log of 0.228 over K1 equals just a bunch of numbers. Check my previous video on using natural log and e to the x, because I give you the answer in that video. And if you want to check your work, the answer should be 1.98 times 10 to the minus 5th per second at 17 degrees Celsius, which is actually choice C in question 20. So I'm hoping this pretty long video helps you with calculating activation energy from that type of equation and how you could organize your information. And I'm hoping this last little tip helps you for question number 20. If this does not help you for 20, please comment on the video or comment on the Google Classroom, and I'll have to break this down a little bit further with my answer key.